All right, this is Recycling and Sustainability of Concrete Structures by James Norris. Concrete is not only the most widely used construction material in the world, but also one of the most resource intensive. Valued for its strength, versatility, and durability, concrete is a staple in modern infrastructure. However, the environmental consequences of concrete production and the challenge of managing concrete waste are growing concerns amid the global push for sustainable development. The production of cement, a critical component of concrete, is responsible for approximately 8% of global carbon dioxide emissions. This statistic is alarming given the increasing global demand for urbanization and infrastructure. As cities expand and buildings age, an enormous volume of concrete waste is generated from demolition and renovation projects. Without effective recycling practices, this waste contributes to environmental degradation, overburdened landfills, and the depletion of finite natural resources. Recycling concrete, therefore, plays a pivotal role in reducing environmental harm, conserving resources, and supporting a circular economy. I'm going to be delving into the processes, advantages, and obstacles related to concrete recycling while addressing ethical responses and assessing global impacts. The discussion highlights how recycling concrete is not just a technical solution, but a necessary shift towards sustainable construction practices. Concrete recycling processes and techniques. Concrete recycling begins with the identification and collection of waste concrete from demolished structures or unused construction materials. This material is then transported to recycling facilities where it undergoes processing. The most common recycling technique is mechanical crushing, in which large concrete pieces are fed into industrial crushers to break them into smaller, reusable aggregates. The processed material, known as recycled concrete aggregate (RCA), can then be categorized based on size and quality and reused in various construction applications, such as base layers for roads, sub-base materials, or even new concrete mixes. Recycled concrete aggregates are generally classified into two types: coarse RCA and fine RCA. Coarse RCA consists of larger fragments typically used for structural fills and drainage applications, while fine RCA includes smaller particles suitable for non-structural applications like pathways or landscaping. The effectiveness of RCA largely depends on factors such as the original concrete composition, the recycling methodology, and the degree of contamination present in the material. To ensure higher quality and performance, advanced separation techniques such as magnetic separators for metal removal, air classifiers for dust extraction, and water flotation for separating impurities are often used. Recent technological innovations have further enhanced the quality of RCA. For example, thermal and mechanical treatments can help remove adhered mortar from the aggregates, thus improving their strength and density. Additionally, mobile recycling plants have emerged, allowing on-site processing of concrete waste, which saves transportation costs and minimizes emissions. All right, here are a few benefits of recycling concrete. Recycling concrete offers a multitude of benefits ranging from environmental and economic to social advantages. One of the primary benefits of recycling concrete is the significant reduction in demand for virgin aggregates. Quarrying and mining for natural materials often result in habitat destruction, deforestation, and loss of biodiversity. By substituting recycled aggregates, we can reduce the ecological impact of extraction activities. Moreover, recycling concrete minimizes carbon emissions associated with transporting raw materials and manufacturing cement, contributing to a lower overall carbon footprint. Waste reduction. With the increasing volume of construction and demolition waste, managing this waste has become a pressing issue. Landfills are filling up rapidly, and concrete waste forms a substantial portion of C&D waste. Recycling diverts this material away from landfills, alleviating pressure on waste disposal systems and which alleviates pressure on waste disposal systems and reduces the need for new landfill sites. Energy conservation. Producing new concrete, particularly the cement component, is energy intensive. The process involves mining, transportation, and heating materials at high temperatures, all of which require significant energy inputs. Recycling concrete circumvents much of this energy demand by reusing materials that have already been processed. Economic efficiency. Utilizing recycled aggregates can offer significant cost savings. Recycled materials are often more affordable than new ones due to lower processing and transportation costs. For large-scale projects, this can result in substantial financial savings. Additionally, recycling initiatives can create local employment opportunities and foster the growth of a green economy. And then material availability. In areas where natural aggregates are scarce, RCA provides an alternative and readily available material source. This is especially beneficial in urban environments where local supply of raw materials can be limited. All right, then a few challenges, and there are a few challenges in concrete recycling. While the benefits are substantial, there are notable challenges to concrete recycling that must be addressed to facilitate broader adoption. First is quality control and performance variability. Recycled concrete aggregates can vary in composition and quality depending on the original structure's age, use, and exposure to elements. Such variability can impact the mechanical properties of new concrete, making quality control critical. Advanced processing techniques and rigorous standards must be implemented to ensure the reliability of RCA in structural applications. And then technical and structural limitations. Despite these advancements, RCA often exhibits lower compressive strength, higher porosity, and reduced durability compared to natural aggregates. These limitations can restrict its use in high-performance structural components. However, ongoing research is addressing these concerns by modifying concrete mix designs and exploring the use of supplementary cement materials to enhance performance. And then contamination and sorting. Concrete waste may contain contaminants such as wood, glass, metals, plastic, and asbestos, which all need to be removed to meet safety and quality standards. Efficient sorting mechanisms and contamination detection technologies are crucial to maintain the integrity of recycled materials. And then regulatory and perception barriers. In many regions, there's a lack of consistent regulations and standards governing the use of RCA. Additionally, some engineers and contractors remain skeptical of recycled concrete's performance, which leads to reluctance in adoption. Public awareness campaigns, education, and demonstration projects are necessary to change perceptions and encourage broader usage. And then there's are some ethical considerations in recycling concrete too. The ethics of recycling concrete extend beyond practical concerns, which touch on moral obligations to the environment, society, and future generations. Environmental justice. Communities near quarries and landfills often bear the brunt of environmental degradation, which face pollution, noise, and reduced quality of life. Recycling concrete reduces reliance on new quarrying and landfill usage, thereby mitigating the negative impacts on vulnerable populations and promoting environmental justice. Resource stewardship and intergenerational equity. Ethical stewardship of natural resources involves preserving them for future generations. Recycling embodies this principle by minimizing resource extraction and supporting sustainable use. It reflects a broader ethical commitment to long-term environmental sustainability rather than short-term economic gains. And then corporate responsibility and transparency. Construction companies have an ethical obligation to adopt sustainable practices and can be transparent about their material sourcing. Implementing ethical recycling operations involves compliance with environmental laws, adherence to labor standards, and ensuring safe working conditions for workers that are involved in the recycling process. And then finally, social equity and access. Affordable housing and infrastructure are critical in developing regions. By making recycled materials more accessible and affordable, concrete recycling can support inclusive development and equitable access to infrastructure, which contributes to broader social justice goals. All right, the next we have global impact and alignment with sustainability goals. Recycling concrete supports a global transition towards sustainable development and aligns closely with several United Nations Sustainable Development Goals, which are SDGs. First, there's SDG 11, which is sustainable cities and communities. Concrete recycling reduces urban construction waste, encourages resource-efficient building practices, and fosters resilient infrastructure. Next is SDG 12, which is responsible consumption and production. SDG 12 promotes a circular economy by reducing resource extraction and reusing materials. And the last one is SDG 13, climate action, which reduces carbon emissions from cement production and diverting waste from landfills, which contribute to climate change mitigation. Globally, governments are adopting proactive measures to promote sustainable construction. The European Union mandates recycling targets and promotes innovation in waste management. In Japan, the construction material recycling law requires separation and recycling of waste materials from construction sites. These policies provide a strong regulatory foundation for sustainable practices. In the US, the Environmental Protection Agency encourages recycling through incentives and public awareness campaigns. States like California have implemented aggressive recycling goals, requiring up to 75% of C&D waste to be diverted from landfills. Municipal initiatives in cities such as New York and Seattle also emphasize sustainable construction with mandates for using recycled materials in public projects. Research and innovation are essential to enhancing the sustainability of concrete. Key developments include green concrete, which green concrete replaces a portion of cement with industrial byproducts such as fly ash, slag, and rice husk ash, which these reduce carbon emissions and enhance durability. It often incorporates RCA, which maximizes environmental benefits. Another one is self-healing concrete. This cutting-edge material contains bacteria or capsules that activate upon cracking, which produce calcium carbonate to seal the fissures. It extends the lifespan of structures and reduces maintenance costs. And the next is carbon capture and utilization. New technologies enable the capture of CO2 during concrete production and curing. CarbonCure and similar companies inject captured CO2 into fresh concrete, where it becomes mineralized, enhancing strength and reducing emissions. Additive manufacturing methods now allow for precise construction using recycled concrete, reducing waste and enabling unique architectural designs. This method is gaining popularity for low-cost housing and emergency shelters. And then finally, smart concrete, integrating sensors with concrete structures allows for real-time monitoring of stress, temperature, and corrosion, which enable predictive maintenance and reduces resource usage over time. And then here are a few case studies. In the Netherlands, the Dutch government's Green Deal initiative has made the country a leader in sustainable construction. Projects like the renovation of the A6 motorway, which used more than 95% recycled materials, demonstrate the feasibility of large-scale concrete recycling. And then in Singapore, Singapore is faced with land scarcity. Singapore has embraced recycling with government support. The Building and Construction Authority mandates RCA use in public housing, and local contractors have also adapted to meet the stringent sustainability criteria. In India, rapid urban growth has made construction waste a major concern. Cities like Delhi and Mumbai have launched concrete recycling plants and are experimenting with policies to mandate RCA in new developments. The Central Public Works Department has issued guidelines to promote recycled materials in public works. And then finally, in Australia, with increasing focus on environmental regulations, Australia is advancing its recycling sector. State governments have introduced waste levies and grant programs to support recycling infrastructure. All right, and then to conclude, the recycling and sustainability of concrete structures are integral to addressing the environmental, social, and economic challenges of the modern construction industry. As urbanization continues and the demand for infrastructure grows, adopting sustainable practices become not just desirable, but essential. Through advanced technologies, supportive policies, and ethical commitment, the construction sector can reduce its carbon footprint and transition toward a circular economy. Concrete recycling presents a compelling opportunity to conserve natural resources, lower emissions, and reduce waste, and promote social equity. It aligns with global sustainability objectives and reflects our collective responsibility to protect the planet for future generations. Moving forward, collaboration among governments, industries, researchers, and communities will be vital in scaling up these practices and ensuring that sustainability becomes the foundation of construction worldwide.